At the end of the last video, I gave a suggestion for a program you might write. Here's a sample solution. The program has 3 functions that all do the same thing, but in different ways. What they're doing is they're comparing list 1 and list 2, and each element in our return list will be 1 or 0. 1 if that element in list 1 also exists in list 2, and 0 if it doesn't. So let's look at the main first. What I've done is generate a couple of lists with a load list function. And their links are 1000 and 5000. This is the load list function. I've set a random seed, and I've created list 1 and list 2, which I'm returning. And they're going to return list of random numbers in range 100 of different lengths. Let's look at the first function here, the loop version. And notice I didn't document. I wanted to just kind of hone in on the code here and not take up a lot of screen room. In the loop within a loop version, we start off with an empty list. The outer loop iterates through each element of list 1. The inner loop loops through each element of list 2, seeing if that item is in there. The function that just used one loop iterates over each element in list 1 and then uses the in construction to set the binary 0-1 value in the return list. And here we have the function with just a list comprehension, which is going to return a Boolean here for each element in list 1. Let's run that and compare the timing. We see that the loop within the loop executed in 0.335 seconds. Single loop for loop executed in 0.00165 seconds. And the list comprehension was just a tiny bit faster. If I actually run this several times, I get slightly different numbers for the timing, but they tend to fall into very close ranges. So keep in mind that clock time is not really process time exactly, because my CPU could be doing other things. Python could be doing garbage collection in the background. Generally what people do if they want really accurate results for timing is that they'll run it many times and then average the results. But in the many times that I ran this, I get very similar numbers. I want to point out one more thing here. And that is, in the loop within the loop version, I could have made it much more efficient by putting a break here. So notice that we're assuming here with result is 0, meaning that the item is not in list 2. Then we start iterating through every element of list 2, and if we find one that's equal, we set result 1. What the break will do is break us out of this inner loop, so we already know it's there's no point in checking the other locations, and bring us into the outer loop. And when we ran that, we see that now the loop within a loop is much more competitive. It's still less efficient than the single loop or the list comprehension, but it's not quite as bad as it was before. Also, you may have noticed these sums that I commented out. I use that for debugging purposes to compare them, make sure that all 3 of my algorithms got the same result. Alright, on to the topic of this video, which is tuples and sets. First, tuples. Tuples are like lists in that they're sequence type, ordered collections of data. The elements of a list or a tuple can be any kind of object, even other lists or tuples. The one big difference between tuples and lists is that lists are mutable and tuples are immutable. There's situations where we need something like a list, but we want it to be immutable, and that's why we need tuples. An example is a dictionary key. The key has to be immutable. Let's look at an example of creating a tuple. If on the right side of the equal sign we have comma-separated values, these will create a tuple. Notice that the tuple is sequential like a list. Notice also that it's surrounded by parentheses, not square brackets like lists. We can index individual elements in a tuple. But notice that we cannot change them, just reinforcing the idea here that the tuple is immutable. When we created tuple T here, we had multiple items on the right and then one tuple on the left. When we do the opposite, that's called tuple unpacking. So on the right, I have the tuple, and I'm going to unpack it into a string, a digit, and a float, and then print those out. A lot of the methods that we've seen on lists and strings also work for tuples. Length, count, and index. We can convert back and forth between lists and tuples with the built-in list and tuple functions. Lists, strings, and tuples have order, but sets are unordered collections of objects. Furthermore, it doesn't allow duplicates. I can create a set with these curly braces, and notice the in operator works on sets. You can also create a set of any iterable, such as a string, with the built-in set function. Notice that there's only one E here. We've talked quite a bit about list comprehensions. You can also do tuple comprehensions or set comprehensions. Because a set is unordered, we can't index into it. We can only use the in operator. Python also supports mathematical set operations like union, intersection, difference, and so on. And you can look those up in the documentation when you have a need for those. I wanted to talk about a sample program where using set functions might be useful. So imagine a situation where you're given an assignment. The assignment involves two large lists. The objective first is to find a third list that contains common elements to both lists. This is how you might write it. So you're going to iterate over list 1. For each number in that list, you're going to see if two things are true. Number 1, that it is also in list 2. And number 2, that you haven't already added it to the list, so you don't want duplicates. And if both those conditions are true, you append it to the list. That works just fine. Then suppose you get the idea, well, maybe I should use a list comprehension. So you start thinking about that, and you have to do this really ugly list comprehension that you don't really want to do. So I have my comment, don't do this. So what we're doing is checking the list at the same time we're adding to it. That's a really dangerous coding practice. In this case, it actually worked, but it's not a good practice, so don't do it. And notice that we got similar function times here. The other objective was to write functions that return items that are unique. So using a loop, we're going to have 2 for loops here. We're going to iterate over the items in list 1 and check that it's not in list 2 and not already in their new list. And then we're going to do the same thing for list 2. Then we also have to have 2 list comprehensions if we try to do this with list comprehensions. And again, the same bad practice, don't do that either. The results here were, again, very comparable. Now let's look at a third approach that uses the built-in set functions. So to find the common elements, we can take set from list 1 and intersect that with the set of list 2. And to find the unique elements, we can take the set of list 1 and do the symmetric difference with set of list 2. Let's look at those times. Those times were just enormously faster than the other approaches that we used. And I'm showing you this example just to keep in the back of your mind that there are times when these set operations may be very useful to you, and they are very fast. Next time we'll talk about dictionaries. Until then, happy coding!